So let's do a bit of recall. I said that energy was the ability to do you remember? Work. And the two definitions that I've given you for work so far, the first one is work equals force times distance. That's a limited equation, though. It only works, no pun intended, if the force and the distance are in the same direction and if the force is constant. Or, I also told you that you could find work if we had a force versus distance or displacement graph. That area was the work. I would use that, Braden, if they gave me a force versus distance graph. But the best and most flexible definition of work is the work energy theorem. It says this: work is equal to the change in potential energy and the change in kinetic energy. What's change in anything? Yes. Let's make a little note here. Delta means final, takeaway, initial. There's a special subcase of the work energy theorem. If we're on flat ground, if the ground is level, will there be any change in height? So will there be any change in potential energy? No. So sometimes you'll see the work energy theorem written like that, but that's assuming we're on flat level ground. Okay. By the way, this equation is actually where everything comes from. For example, don't write this down. If I have change in potential plus change in kinetic, if I have a closed system where there's no outside sources of energy, then the amount of work I get out is zero. What's change in anything? So I can write this as PE final minus PE initial plus KE final minus KE initial. And now if I plus that over and plus that over to this side, I get KE initial plus PE initial equals KE final plus PE final. What's that? Hey, there's the law of conservation of energy. It's a consequence of if you have a closed system, you can't get free energy out of it, free work out of it. So everything actually comes out of the work energy theorem. That's hashtag nerd trivia. I'm not going to test you on that. So where can you use this? Example 1. I like example 1. I like example 1. A cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. Okay, you know what? That means that M equals 72.2 kilograms. There's our total mass. Hope I did that right. I think I did. If she's pedaling over level ground, how much work would it take for her to increase her speed from rest to 5 meters per second? Nicole, what's this question asking me to find? How much? Okay, don't write this down, but look up. My first thought, Kevin, would be to go work equals force times distance. But Nicole, is there a force in newtons given in this question anywhere? Is there a distance in meters given in this question anywhere? Is there any indication that I could figure out a force or a distance? No. So I would, in my mind, scratch through that one. Then, if they had given me a force versus distance graph, I would find the area underneath it. But let's be Captain Obvious here, Nicole. Did they give me a graph? Then I go to the work energy theorem, my third definition of work. So write this down. Work is the change in potential plus the change in kinetic. This is the 3-step sequence I go through every time I see how much work. Oh, Nicole, underline the word level and the word ground. Is there a change in height at all in this question? So is there a change in gravitational potential energy in this question? So I can go, ha-ha! Oh, by the way, though, if they also wanted me to ride up a hill, I could include it, which without much, no pun intended, work. What's change in anything? What's change in anything? Final. So change in kinetic is going to be kinetic final minus kinetic initial. You know what? I'm going to go like this. Work is going to be a half mv final squared. Why didn't I bother writing minus a half mv initial squared? Because isn't okay. So it's still change in anything. It's final minus initial, but initial is 0. How much work would it take for this biker to go from 0 to 5? 0.5 times 72.2 times 5 squared. Which is what? Can I do some? No, yucky. $903? Can you give me the whole thing? 902.5 joules. So what this means is her bike gained that much kinetic energy. Where'd that energy come from? The food that she ate, because it's got to come from somewhere. So this is why cycling will cause you to burn some calories, to burn some energy. But you may have noticed when you're biking that once you're biking fast, the effort it takes to go even faster is way more. By how much did we increase our speed if we went from 0 to 5, Nicole? By how much did we increase our speed? Be obvious, yeah? How much are we increasing our speed in part B? Should be the same answer, shouldn't it? No. This is where I told you that squared dominates your life. Okay? So it's going to be the same argument. We're going to say how much work, force times distance doesn't work. There's no graph. We would go with this, except now we're going to have work equals a half mv final squared minus a half mv initial squared. This time none of them cancel. And AJ, can you see final is 10, initial is 5? It's the same 5 meter per second increase. But if we actually plug in the numbers here, work is going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. What do you get? I think you're going to get 2,700 and something. More specific, 2,700 and... So you can see same increase. In fact, you know what? I think if you go 2707.5 divided by 902.5, it works out to exactly 3. Same 5 meter per second increase, but Nicole, 3 times the energy to do it. Oh, also, the M does not cancel, although there's an M in everything on the right. Is there an M in work? This is why the heavier you are, the more energy you burn exercising. This is why little kids can run around for hours and hours and hours, but when you're a grown-up, you can't do it anymore. You just can't. Okay? Little kids, smaller mass. Did I see a hand up? No? Okay. C. Same 5 meter per second increase, but trust me, it's going to be even bigger than this. Work is going to be a half 0.5, 72.2, 15 squared minus a half 0.5, 72.2, 10 squared. What do you get? Think you can get something in the 4,000s? Think. 4512.5. This also explains why in a car you can't just step on the gas and keep going faster and 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 faster. Eventually, the change in kinetic energy will equal the amount of energy the engine is capable of putting out. That's your top speed. Okay. This is the work energy theorem. You also use it in rocket science. So example 2, I'm going to doing this for a model rocket. If we had got to our orbital mechanics unit, we actually would have done this for real life rockets. How much work really is, how much energy and rocket fuel do I need to send something into orbit? So here, a model rocket reaches a height of 340 meters when launched. If we were doing this with the big people, we would say an orbital height instead. The speed of the rocket is 85 meters per second. How much work does the rocket engine do on the rocket? Alex, what's this question asking me to find? How much?
Speed.
Keep reading. Keep reading.
Work.
How much work? Don't write this down. My first thought would be that. Well, we're going up, and so I might be tempted to say the force is mg, and there is a distance. But they also gave me a speed, and I haven't factored that in yet, so I don't think so. My second thought might be it's the area underneath a graph. Did they give me a graph? I'm going to use the work energy theorem. It's the change in potential plus the change in kinetic. Alex, is there a change in height in this question? How high are we when we start? How high are we when we finish? Yes, so don't cross this out. Is there a change in speed? How fast are we on the ground? On the ground. Yeah. How fast are we at top speed? Is there a change in speed? Okay, none of these are going to cross out. What's change in anything? Final minus. So I'm going to break this into PE final minus PE initial plus KE final minus KE initial. Although you just told me I can cross out Prince Edward Island, of course I can, and I can cross out KEI. Yay! If we weren't on the ground to begin with, it'd be easy enough to factor that in, or if we weren't starting at rest, it'd be easy enough to factor that in. So how much work, or let me say this differently, how much chemical energy does the rocket engine have to provide to this system? It's going to be mgh final plus a half mv final squared. Does the m cancel? No, there's an m in everything here, but not in work, which makes sense. It takes way more energy to put a bigger rocket up. Of course you need more rocket fuel. So it's going to be 0.15 times 9.8 times 350 plus 0.5 times 0.15 times 85 squared. How many? Yeah. 340? I was just giving it an extra 10 meters because I wanted it to go higher. Any of you have model rockets? Played with them? Okay. I have a model rocket back there. I'm trying to think of a way within the COVID protocols that we can go to the backfields and launch one on a sunny day. I might end up doing it on the turnaround day or something like that because it's great physics. But it's weather dependent. If it happens to be rainy, we're out of luck. Rocket science, sorry. What do you get? How many joules of energy will this take? I have no idea here. Elias, what'd you get? 1056.375. Anybody else? Ooh, I'm not seeing nods.
I got 1,041.675.
1041.675? Okay. Maybe you use the 350 that I wrote instead of the 340. So blame me. Totally my fault. Sorry, Alec, what was the answer?
1041.675.
What does that mean in like real world terms? That's how much chemical energy that rocket engine has to be able to put out. This is ignoring air resistance. In real life, you'd have to also factor in air resistance if you're trying to launch something into orbit, but it starts here. It starts with the work energy equation, the work energy theorem. Oh, also in real life, you'd have to factor in, as you get further from Earth, what happens to the 9.8? Yeah, and so you can't actually use this equation. Gravitational potential energy, once you leave the Earth, it's not MGH, it's a much more complicated equation, which we would normally get to and deal with, but it's one that it includes the radius, the distance you are from the center of the Earth, the mass of the planet that you're orbiting, and the mass of the object that you're trying to launch. So that's the, with a changing gravitational field, gravity equation, a potential energy equation. I like example 3, I like example 3, I like example 3. Example 3 is a nice question. Blah, 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 blah. Okay. Austin, what's A asking me to find? Sorry? How much work? And again, my first thought, don't write this down, would be, well, work is force times distance. Do you see a force in this question anywhere? In newtons? Do you see a distance in meters? No. My second thought, Austin, would be, well, it's also the area underneath a graph, a force versus distance graph. Do you see a force versus distance graph in this question? No, you're saying? The work energy theorem. Although, Austin, over level ground, I can use the special subcase of the work energy theorem. I could have skipped writing change in potential. What's change in anything? So this is going to end up becoming a half mv final squared minus a half mv initial squared. Are any of these 0? Oh. Okay. We're going to get a negative answer. Now, what does negative work mean? It says the car has to lose kinetic energy before it can stop. So this negative is not really a directional thing. It's a magnitude thing. I'm okay with the negative here. It's going to be negative 0.5, 1250, 35 squared. And I get negative 765,625 joules of energy. Okay. Where does that energy go? It's got to go somewhere. Where does it go? It heats up the brakes like crazy. Oh, unless any of you have a hybrid or an electric car. Okay. For hybrids, I've test driven a Tesla. As soon as you take your foot off of the gas pedal, although they won't let you call it the gas pedal because it doesn't use gas, they call it the go pedal. It doesn't use gas. So as soon as you take your foot off the go pedal, it feels like you're hitting the brakes, even though you're not. Because with electric vehicles, the energy goes into recharging the batteries instead of heat, which is one of the reasons they get such good mileage. Okay. In fact, with an electric vehicle, if you start, say, at the top of the Coquihalla Summit, with a charge of, let's say, 65%, if you play your cards right, you can find by the time you get to the bottom, you've got a charge of 71%. You've actually made more energy going down than you spent driving forwards. Okay? It's a really neat system. And had we had time, one of our final lessons this year would have been, I would explain to you how it's possible. It's called a back EMF or a back voltage, how you can get energy back from an electric motor, but no time. If you're bored sometime during a blended block, come talk to me and I'll walk you through it. It'll take me about half an hour, but it's way cool. B. Ooh. Huh. Justin, what does B want me to find? Force. What else did they give me in B? What did I find in A? Is there an equation that has a work and a force and a distance in it? Can you get the force by itself, please? So while normally when they ask how much force, I'd be tempted to go, who's winning? Who's losing? This is a job for everybody. No. Now I'm broadening my toolbox and I would say, I just found work. They gave me a distance. I can figure out the force. By the way, what's creating the force? You already alluded to this. You said friction. Okay? It's going to be, I'm going to chuck the negative. The negative now is saying that the force is in the opposite direction of motion because force is a vector, but I'm just going to find the magnitude. So I'm going to go 7, 6, 5, 6, 2, 5 divided by 82. And I get 9,340. I'll go 9,340. And that's a force, so it's newtons. Cool. AJ, what does C want me to find? Hey, what's mu? I don't know what's mu with you. What did I find in B? Which force? Is there an equation that has a friction and a mu in it? Friction is what times what? Get the mu by itself, please. Friction is going to be 9,340, but I'll use my answer button. I don't know the normal force. Wait a minute. Are we on level ground? You know what the normal force is equal to? It's going to be mg. Okay? So it's going to be 9,340, answer button, divided by 1250 times 9.8. Divided by 1250 times 9.8. And I get a mu of 0.762, which is pretty high for tires. It says for you to actually accomplish this, you better have some good tires. Most tires have a mu on pavement about 0.6, but there's various factors. You may have noticed on a hot, sunny day, pavement is way stickier than it is on a rainy, wet day, or even on a cold winter day. In the summertime, when it's over 30 degrees, pavement gets pretty sticky. Okay? But there's a nice question, and look at all the stuff we pulled in the work energy theorem. We pulled in the other definition of work. We pulled in a little friction is mu times the normal force. I like that. Example 4. Alec, you made my day. What did you just say? I did a question similar to this in Physics 11 with you in the kinematics unit, where I said an RCMP officer is investigating a car crash. We had the length of the skids, but the problem was at that time you didn't know very much physics, so I had to fake things. I don't know if you remember, Calvin, I said the cell phone picked up the sound of the skids. I had to give you time. Okay, which was really garbage. In real life, there's no way the cell phone by a fluke would pick up the sound of the skid marks that the person was talking. You know, I had to make that up, Elias. I apologize. And I promised you last year that we would revisit the question properly, and we would have after spring break. Did things go a little weird after spring break? I'm keeping my promise here. This is how they would do it if you were an RCMP crash scene investigator or police crash scene investigator. An RCMP officer is investigating an accident. Car has struck a pedestrian at a school crosswalk, so we're in a school zone. There's no witnesses. The officer measures mu to be 0.65, and they have a device where they can do that. They can measure the coefficient of friction at that location. So the skid marks are 49 meters long. Should the RCMP press charges against the driver? So I like this question because it's useful and it's cool. So I think I'm going to say I like this question, I like this question, I like this question. We're going to start out really weirdly. We're going to start out by saying, hey, work equals work. Oh, I should say, by the way, what's this question asking me to find? Because it's not quite so obvious. Which one? Initial or final? What's V final of every car accident ever? Okay, so I'll make a little note over here. VI equals, that's what I'm trying to find. Okay. Why did I write work equals work? I'm going to use both equations for work. I'm going to go force times distance, and that's where the 49 is going to go, equals change in potential plus change in kinetic. Austin, if there was a hill, if this crosswalk was on a hill, I could handle it, but I don't see any hint of a hill in this question, so I'm going to... But otherwise, I would just have to calculate the change in elevation that the skid marks go through. What's change in anything? Okay. Oh, final is 0. Right?
Right.
Now, do you notice on the right there is a negative? On the left there isn't, but wait a minute. Are the force and the distance in opposite directions? Technically, this is negative as well. What I'm really going to say is on the next line, Austin, I'm going to get rid of both negatives. Okay? On the right-hand side, I'm going to have mv initial squared over 2. And there's my VI. On the left-hand side, the D drops down. Which force? Which force brings the car to a stop? Friction. Friction is what times what? I don't know the normal force. Oh, are we on level ground? Okay, so I can say this. Oh! What do you notice? What about the 2 M's? That's actually really important. If that wasn't the case, a car accident, a person who was a lawyer could simply claim, oh, a bunch of gasoline leaked out after the crash. Your masses are not accurate. Or they could claim half the tank leaked out or something like that. Or they would. So the fact that the mass cancels takes away a lawyer possible arguing point. What are we trying to find? Times by 2, and then square root. Two mu g d. I'm betting that would be just the equation that would be given to the investigator. They wouldn't derive it like we did. But let's find out how fast this person was going. Oh, I wrote squared, sorry. We square rooted, so I should cross out the squared, shouldn't I? VI is going to be the square root of 2. What was mu? 0.65?
Yeah.
9.8. How long were the skid marks? What do you get? 620. Oh, square root, Mr. Duke. Sheesh. That's a little fast. So a school zone is 30. This says 25. Or does it? This is, okay, this is 25 meters per second. How do we convert that to kilometers per hour?
Oh, yeah. I think the first we hit 10.
Right? For those of you who played Monopoly, you'll get that joke back in the day. Anyways, yeah, this person wouldn't have much of a defense. Oh, and by the way, that's minimum speed. Could they have slowed down before they started skidding? Yeah. In fact, they probably did. Now, it's become a little tougher now because most modern cars don't skid. You have a system, the anti-lock brake system just prevents skidding, or you might get short skid mark coasting, short skid mark coasting. So I'm sure this has been modified over the years, but it starts with this concept at least. Okay. Oh, sorry, yeah. Driver will go to jail. I should add, because the question asked, can they press charges? Yes. And this method did not require the miracle of the cell phone picking up the sound of the skid mark so that you had time. I think this one I'm going to pause my YouTube. Where is it? Right there. So we watched a video of somebody being an idiot. The initial was 220 miles per hour. I'm going to cheat. Convert 220 miles per hour to meters per second. Which is 98.35 meters per second. The final was 100 miles per hour. Convert 100 miles per hour to meters per second. You all know your phones can do these things, yes? It's handy. 44.7. All right. A says, how much energy is lost as the motorcycle slows? I didn't see a hill in the video. The road looked pretty level. So I think all that was lost was the change in kinetic energy. What's change in anything? So this is going to be a half mv final squared minus a half mv initial squared. When I found this video on YouTube, I did some Googling of various high-end bikes, and I'm making some guesses, but Bike and Rider is about 300 kilograms. I'm probably within 30 kilograms either way with my guess. I'm close. So it's going to be 0.5 times 300 times 44.7 squared minus 0.5 times 300 times 98.35 squared. Which is what? I want to find out myself. I'm going to type this in. 0.5 times 300 times 44.7. You get a negative answer, which you should, because the bike had to lose energy. You get negative 1151194.875? Okay. So negative, I'm not going to round this off because I'm curious what's going to happen with some of this. So negative 1151194, negative 1151194.875. Where'd that energy go? Yep. Some sound, mostly heating up the brakes and the engine. Yeah. C. Ooh, Cole, what does C want me to find? How do I find power? Power is? Hey, work is the change in kinetic energy. It's this number. We need the time. Let's pause the video recording again. So watching the video, T equals 16.5 seconds-ish. So up here, it's going to be 1151194.875. Answer button divided by 16.5. How many watts of power? I've still got a negative in my answer because it's an energy loss. I'm just going to ignore the negative for the rest of this on my calculator. And I get 69,700 and I'll go 69,800 negative, well, not negative, 69,800 watts of power. Or to put this into perspective, D, how many 60-watt light bulbs could we light with this wasted energy? Divide by 60. 1,163. Are you starting to see why regenerative braking makes such a big difference? If you can bleed even half of that energy off and back into the system, hey, take it. Okay? Electric cars. I like example 4. I like example 4. Example 4 is a nice question. A 5.2 kilogram rocket car. Is this the last one? I think it is, isn't it? Yes, it is. Good. A 5.2 kilogram rocket car is initially at rest. I'd probably mentally or actually underline at rest because that's important. On a frictionless horizontal, so we're on a level ground surface. The engine is ignited, and the graph below shows the thrust force, F, versus the distance traveled, D, for the car. So it looks like for the first 15 meters, we get a lovely thrust of 160 newtons. Why do you think the thrust dies off after 15 meters? Why? Well, yeah, I think motor is burning out. Right? Rocket engines are typically chemical engines with a pretty short lifespan. Okay. B. Find the speed of the car after 15 meters. Find the what? Speed or velocity? What does it say? Which probably means a scalar approach. Also, I don't see a VF or an A or a T. I mean, VI is 0, and this is sort of a distance. But what kind of a graph is this? What versus what? Force versus distance. I'm going to use work. I'm going to start out again by saying work equals work. Well, duh. No, here's what I mean. The area underneath the graph is going to be equal to the change in kinetic energy. Why didn't I bother including the change in potential energy? Level ground. Okay? What is this area? Well, it's this shape here. What shape is that? Because it's just up to 15 meters. We're just going right to here for now. It's a rectangle. How do I find the area of a rectangle? Yeah, length times width, base times height, whichever way you want to call it. It's going to be 15 times 160 or 160 times 15. That equals a half mv final squared. Oh, why didn't I bother writing minus a half mv initial squared? At rest. Okay. What were we trying to find? Oh, Now, by the way, we could have done this using velocity and acceleration and forces. 3 lines and we're nearly there, because how would I get the v by itself? Divide by m times the 2 over, or divide 0.5, and that gives me v squared. So square root. It's going to be 2 times 15 times 160 divided by the mass. Square root, and do you mind? I'm going to put the VF over on the left because that's where we're used to seeing the thing by itself. If you didn't, that's fine. They told me the mass, didn't they? I hope.
Yeah, 5.2.
5.2. 2 times 15 times 160 divided by 5.2. Square root. Car is going 30.4. C. Now find the speed after 25 meters. I can do that. Sure. It's going to be the same argument. We're going to say work equals work, and it's still going to be a half mv final squared on the right. But this time the area is going to be rectangle plus triangle. Is that okay writing it like that? You can write the word rectangle plus triangle if you want to. The rectangle we already did. The rectangle, Elias said, was base times height or length times width. I don't care which. How do I find the area of a triangle? If you're not sure, it's on your formula sheet somewhere. Probably somewhere where there's a picture of a triangle. Half the base times the height, or I usually go base times height divided by 2. Oh, what's the base of this triangle? What's the height? 160. So it's going to be 10 times 160 divided by 2. That equals a half mv final squared. That's terribly messy, Mr. Newick. You know what? I'm going to crunch left side, turn it into one number. Actually, I might be able to do it in my head. 10 times 160 divided by 2, that's going to be 80 times 800. 15 times 160, well, 5 times 160 would be 2,400. 30, is it 3,200? Yeah. That equals mv final squared over 2. Half mv squared. Divide by m times by 2 square root. How fast are we going after 25 meters? Should be going faster because there's still a force being applied, just not as much as before. So I don't know how big a jump it'll be in the final few meters, but you should get an answer bigger than 30.4. What'd you get, Cole? 35.1. Anybody else? People nodding? That's the work energy theorem. I can use it to figure out missing speeds from graphs if I need to by realizing that work equals work. The area equals the change in kinetic plus the change in potential. I can use it to do a little rocket science, a little RCMP investigation. What's your homework? 1 is good. 2 is good. 3 is good. Armand, just give me a couple seconds. I'm almost done and I'll pay attention to you. Let's do 4B. I figure if you can do B, you can probably do A, you can probably do C. Five is good. 5 is just like the question that we did, but instead of speeding up, we're slowing down. So you're going to get the VI by itself. See if you can figure it out. 6 is just like we, you know what? Let's do B again, just for giggles. You can skip 8. 9 is good. Let's do B again. Okay. And that, my angels, is the work energy unit. You are going to get a study guide. When will you get the study guide? Tomorrow. I'll also be giving you a take-home quiz tomorrow. And we'll start looking at things moving in circles tomorrow. Yes, we'll start spinning in circles. I've been doing that all year. Nope, different.